Hello, this is the Code Critics. In this episode, we are going to look at list comprehensions and their variations. Let us start with two simple examples of list comprehensions in comparison to for loops. Given is a list of numbers, and we want to compute the absolute values of those numbers. We could do this in a for loop, where we iterate over the numbers, compute the absolute values, and append the result to a new list, which then would contain the absolute numbers. The same can be implemented with much less and simpler code using a list comprehension. The structure of the for loop is maintained. There's still the for and the in keyword, but the function call of the abs function has moved to the front, and we don't need to call append anymore. List comprehensions are shorter, easier to read, and for simple, fast functions such as abs are about twice as fast as for loops. As a second example, let us assume the list of numbers can contain none values, a common case in data science projects. We still want to compute the absolute values, but need to filter out the none values first. Here's how we could implement this using a for loop and an if statement. Since the filtering of items from a list is such a common use case, list comprehensions provide support for this in the shape of an if clause. As you can see, the structure of the list comprehension is largely identical to that of the for loop when removing the line breaks and colons. As before, the function call is at the front of the list comprehension, and there is no need for the append function anymore. The generic pattern to replace a for loop by a list comprehension is as follows. We have a result list y's that is constructed by iterating over the elements x in x. If a condition c on x is true, we call a function f on x and append the result to y. We can replace the rectangular brackets by curly brackets and get a set comprehension, where the results are not stored in a list but in a set. Similarly, there is a dictionary comprehension that follows the same pattern but uses key value pairs. Note that there is no tuple comprehension with the same syntax. Putting round brackets around a comprehension expression produces a generator, which is a completely different thing. More about generators in a different video. However, we can use the tuple class to implement a tuple comprehension. One disadvantage of the list comprehension used to be the case where we need to compute some function f of x that is used as a result and is used in the if clause as well. Before Python 3.8, the function needed to be computed twice, which would be slow if the function is time-consuming to compute. Since Python 3.8, we have the walrus operator, which allows us to assign the return value of f of x to a variable and to reuse it. We will see an application of this later. Another common pattern that I want to mention here are nested for loops or lists. Nested for loops are supported in list comprehensions and follow the same syntax. Removing the line breaks and colons of a for loop and flattening it out essentially leads to a list comprehension, with the only difference that the function call appears at the front and the append is not used. Similarly, list comprehensions can be used to create lists of lists or many other kinds of nested data structures, such as sets of lists or dictionary of sets, for instance. Here is a little brain teaser. This list comprehension computes the prime numbers within the first 100 natural numbers. It is a highly inefficient implementation, but fun to implement and to figure out. For a more practical example of comprehensions, we take the following use case. We have a text file with names of people in it, each line one name. For a given search string, we want to find the line with that name. But some names are very difficult to remember, such as mine, and we need some kind of fuzzy matching in the case that the search string is not a perfect match. We could use a regular expression for this purpose, but writing a regular expression to describe different potential spellings of names would be very cumbersome. We need something better suited, and a common technique is the usage of n-grams. This is how it works. We move a sliding window, let's say of size 3, over the text and extract sequences of 3 characters, 3 grams, such as MAE, AET, ETS, and so on. Note that we convert the text to lowercase, since we want to ignore uppercase or lowercase when matching texts. If we do the same for the other 2 spellings of my name, we find, not surprisingly, that there is some overlap between the n-grams. We can use the ratio of overlapping n-grams as a similarity measure of strings and implement a fuzzy matching. The first function we implement is n-grams, which converts the text to lowercase, iterates over positions in the text, and extracts n-grams of size 3. Note that we use a set comprehension to return the set of those n-grams. Next, we implement the matching function. Let's assume we have already computed the n-grams for a query string. We call this parameter qgrams. To compute the matching n-grams between the qgrams and the text, we compute the n-grams for the text and construct the intersection of the 2 sets of n-grams. Easy. The function returns the ratio of the numbers of the matching n-grams versus the number of n-grams in the query string. A value of 1 means we have a perfect match, and a value of 0 means there are no matching n-grams at all. For instance, if we match Mechke with Matschke, we get 0.57 as a ratio or similarity value. In general, 3 grams are a good choice, but for short texts like these, 2 grams would work better, while for long texts, 4 grams can be beneficial. It would be easy to compute 2 grams, 3 grams and 4 grams together to be more robust in the case of texts of varying length. Finally, let us implement the find function to retrieve matching lines from a file. The function takes a string query, a file path, and a confidence value CF. We want to retrieve only lines with a matching value greater than that confidence value. The implementation is simple. First, we compute the n-grams for the query. Then we open the file, which returns an iterator over the lines of the file. And then we use a list comprehension to extract all lines that match the query with a similarity value greater than the confidence value. Note the usage of the walrus operator here. The computation of the n-gram match is expensive, and we don't want to calculate it twice. The list comprehension produces a list of tuples, with the matching value first and the line second. Usually we want to see the best matches first, and therefore return a sorted list. Using list comprehensions allows us to make certain changes easily. Let's say the file contains many identical lines, which would lead to many identical matches. Simply changing the list comprehension to a set comprehension by replacing the rectangular brackets with curly brackets would remove all identical matches from the results. Instead of searching for names in the file, let's do something more practical and implement a fuzzy grep tool. Here's the main function. We read the query string via input and check its length. If the query string is shorter than 3 characters, we can't compute n-grams and end the search. Otherwise, we call our find function with a query string and a file path. For this example, we use the implementation of our fuzzy search code in fuzzy.py as a file. Finally, we simply print out the matching lines and their confidence values. If we run fuzzy grep and search for fpath or lines, we get the following output. How cool is that? To summarize, list comprehensions are underutilized. Whenever you see or write a for loop, your first thought should be, can this be replaced by a list comprehension? Despite being commonly called list comprehensions, there are actually set and dictionary comprehensions as well. Watch out for tuple comprehensions that require a different syntax. Comprehensions tend to make code more readable. Be careful with nested comprehensions though, which can be messy. Finally, avoid side effects such as changing global variables, closing files, and other side effects in comprehensions. Side effects are common and somewhat expected in for loops, but not in comprehensions. That's it. Thank you for listening.